start with an introduction about RDMA technology, and I will continue talking about the motivation that we have in the storage world to use RDMA, and I will finish with an examples from storage protocol that using RDMA. So RDMA is a remote direct memory access. It's actually a remote version of DMA. It provides you the ability of accessing directly the memory of a remote host without involvement of both side CPU and operation system. People say it's a fast and efficient way to move stuff from one server to another, and in our case, these stuff are storage protocols. It was first created and implemented in 1999 with the InfiniBand protocol. Later on, Rocky and iWarp came along. The main characteristics of RDMA technology are high bandwidth. Today we can reach 100 and 200 gigabit per second if you have support for PCI Gen 4, of course. Super low latency applications that are using RDMA can reach less than 3 microseconds. The technology provides you a zero copy of the data transfers. There is a full CPU offload. Actually, the data is transferred by the hardware accelerators that reside in the adapters. There is an option to use a kernel bypass feature that actually gives user space application direct access to the hardware. We have also quality of service and asynchronous message transactions. After we understood what are the basics of RDMA characteristics, let's talk about the primitives of RDMA. So the first primitive is a queue pair. We call it QP. It's actually a pair of queues that used for posting a work request to the hardware. We have 4 types of queue pairs. The reliable connected QP called RC. It's similar to what you know as TCP also from the reliability point of view. We have a UD queue pair that is similar to UDP, and we have a combination of both of those. We have a completion queue that is used for reporting work request completions to the host. The application can ask for interrupt-driven notifications, or it can poll the CQ to get it faster. We have a memory region, we call it MR, that describes a memory area and gives it relevant permissions for performing DMA and RDMA operations. We have a protection domain that it provides an association between queue pairs, memory regions, and gives another layer of protection to the host memory. So I summarized the basic operations of RDMA, and I categorized it to 2 main groups. We have the messaging group that both sides are aware of the transaction. So we have 2 basic operations that we use. The first one is posting a buffer for receiving data from the wire. And the second one is sending a buffer to a remote peer that previously posted a receive buffer to receive this data. We have also a memory registration operation called regmr, and that I will explain about it in the next slide. For now, it's just to make an example for the need for the one-sided operation. We use memory regions in order to perform RDMA read and RDMA write operation. RDMA write operation is copying a local buffer that is described by a memory region to a remote buffer that also described by a memory region and a key. RDMA read is a copy of a remote buffer to a local buffer. All of these operations are one-sided operations, and only one side is aware of the operation. The other side doesn't know about it. So memory registration, why we need memory registration, I summarized the main reasons. So the first reason is to avoid data corruptions. For example, one of the steps of memory registration is to pin the pages to the RAM in order to avoid data corruption. The second reason is to protect from unwanted access to this memory. And the most important reason is to map the addresses that we get to the language that the hardware can talk. And this is a DMA language. So we get a list of page and we need to DMA map it to the addresses that the hardware can access. The memory registration operation is quite heavy and it includes allocation, pinning, translation, and so on. So we need to in order to maintain very good performance, we need to think how we can utilize other layers in the way and use a faster registration. So, for example, in the kernel space, we receive the buffer from the user, and the user is allocating the buffer and passing it to the kernel using a system call. And the block layer provides this buffer in an object called BIO, or a scatter gather list. And it also pins the pages to the RAM and actually make sure that there will not be a data corruption. So all we have to do is only allocate some memory region and map the addresses to a language that the hardware can talk. And this we can do with very fast and small work requests that we post on the send queue, and we don't harm our performance. So here we have an illustration of the object that describes this memory registration, and we use IBSG that includes key, address, and length. After we did a small introduction for RDMA, and we understand why we understand the capabilities of RDMA, why we care about RDMA in the storage world. So in the morning, we saw that the storage media and the data is growing faster and faster every year, every month. And if 10 years ago we had hard drives that could access the storage in tens of millisecond order of magnitude. So in the last few years, we have SSDs and we have NVMe devices that can reach less than 50 or 20 microsecond. And the next generation storage persistent memory can even be better and can reach below 5 or even 1 microsecond. So the motivation for that is we have very fast storage, and we don't want that the network will be the bottleneck of the I/O operation. So here I summarized some of the applications and the protocols that are using RDMA. We have in the file system world, we have the SMB Direct and NFS over RDMA that are showing very good performance. In the block storage, we have ICER and SRP that are based on the SCSI protocol. And of course, we have the NVMe over Fabrics that is using RDMA also. I don't want to return about the topics that were spoken earlier, so I just say a few words about that. NVMe over Fabrics standard was completed in June, and we have RDMA protocol is the part of the standard, and we have an example in the wire protocol. We use keyed SGLs, scatter gather elements that has keys, and it's integrated in the protocol. And also we have fiber channel and TCP transport layers that implements NVMe over Fabrics. We spoke about NVMe in the previous talks, but I want to talk about a little bit about how an NVMe transaction is done. So in order to perform an NVMe transaction, one should create a submission queue and a completion queue. It should enqueue a small operation in the submission queue, this entry called submission queue entry, and it describes the I/O. And after posting this submission queue entry, the host should ring a tiny doorbell in order to inform the hardware that you have some work to do, so please do it. And the hardware will fetch the command and will fetch the data, and it will perform the operation. And in the end of the operation, it will post and in queue some completion element, and will inform the hardware, the host, about the end of the operation. And exactly as the queues that we talked about in RDMA introduction, we can poll the completion queue, or we can ask for interrupt-driven completion. So this is exactly what I described in the beginning of the talk. It's very similar to how RDMA works, right? We have a pair of queues, exactly like in RDMA. In RDMA, we have another queue to receive things because it's a networking protocol. And after we see the great mapping between the queues, we have a lot of potential to get good performance and to do interesting stuff that I will explain and demonstrate later. I want to show a fast example of how an NVMe over Fabrics transaction using RDMA. So when the host generates a request and sending the request to the NVMe over Fabrics initiator driver, the initiator driver registered the memory and sending a command capsule that contains the submission queue entry and some description of the data that should be transferred, and post-send an operation to the other side. The target side will receive this completion and will allocate the needed data, and will perform an RDMA read operation. If we are doing write, I/O write, the target does RDMA read and copies the data from the initiator, and then it will post a command to the backing storage that doesn't have to be NVMe. It can the NVMe over Fabrics target can expose different types of media. So after we receive a completion from the underlying storage, we post a command response capsule that says the status of the command, and we can free the memory that we allocated for this transaction. And when the initiator will receive a completion of the response capsule, it will inform the layers above it about the finish of the transaction. So the read operation is exactly the same, except that the target side performs RDMA write instead of RDMA read, and will write the data, fetch the data from the storage device. So what are the challenges that we have in the storage world that we can find the solutions with RDMA? So the main challenge is to maintain the performance that we have with direct attached storage. The second challenge is to reduce the memory footprint. This can be done by sharing resources. Another challenge is to scale. We want to scale, we want to grow, data is growing, we want to have a very fast network in order to adapt to the data that's growing every day. We want to save money, we want to build cheap storage systems, and we want to save CPU cycles. We want to allow the CPU to do other stuff than only doing I/O operation of NVMe over Fabrics or some different protocol. So as you saw in previous talks, NVMe over Fabrics performance is great. We have I borrowed this slide from Samsung Research that posted a year ago, and we can see here the comparison between direct attached storage and NVMe over Fabric storage based on RDMA and the traditional iSCSI. And we can see that almost in every graph that we show here, that direct attached storage and NVMe fabric storage are pretty much the same, gives the same performance, except maybe from latency of one I/O operation with one queue depth. And the iSCSI is not comparable for these two protocols. So can we do better? So if we see that we have such a good performance, can we do better? And the answer is yes. Yes, we can. So I summarized two features that we can implement, and we are implemented them. And in order to become even better than we are now. So the first one is interrupt or completion moderation. Somebody can call it coalescing. It's a technique in which the event that normally should trigger a hardware interrupt are held in the hardware. You say the hardware, don't give me an interrupt immediately, stop for a second and wait until you have enough work for me to process, or some timer will be triggered. And the measures that we did are amazing, and we get more IOPS, like 2 million or 3 million IOPS more with this technique. The problem with this technique is for latency of a single I/O, right? Because if you have a single I/O, you will pay the timeout that will expire. So in order to overcome these problems, we are developing, actually, we have a code from Sagi, that is the maintainer of NVMe fabrics, that is doing this moderation in an adaptive way. There is an algorithm that calculates the needed moderation, and according to the IOPS that we receive in the last second or so. So this is a work in progress, and I hope this will be pushed soon to the Linux kernel. The second feature that can improve performance is register a non-contiguous buffer. Not all the buffers that we receive from the application are contiguous. Sometimes the I/O vector, every element of the I/O vector has its own length, and then we need to map a non-contiguous buffer. So we want to save the block layer. The block layer, when it sees such a I/O vector, it bounce buffers it, and it costs CPU cycles. There is a copy in the way, so we have hardware that can map and can register indirect buffers. We also implemented it in the Linux kernel. We have implementation in ICER and also in SRP and NVMe fabrics. We submitted the patches for NVMe and SRP, and I hope they will also be pulled soon. So please try it. Another challenge that we want to fix is we want to reduce the memory footprint. So let's take an example for NVMe fabrics. So we have a lot of queues, right? Let's say we have a target subsystem that 100 initiators are connected to this target, and each initiator opens 64 queues, or even it can open more. And each queue has a queue depth of 128 elements, and this starts to be a huge memory footprint. So the connections are very cheap, but the problem is that we need to post and receive buffers for incoming data, and this starts to be a big problem if we have this kind of scale. So the solution is to use a shared receive queue. Not every initiator from these 100 initiators that connected are sending I/O in every second. Sometimes initiator number 1 is sending, sometimes initiator number 10. We can share these buffers among all the data that will be transferred. So currently the implementation of NVMe fabrics uses one shared receive queue per adapter. This is not such a good solution because there is a lock contention in the data path. There is no parallelism. We have a better solution that we submitted 2 months ago, and we are now in the second phase of it. We create a shared receive queue per core, and or per completion vector, and this gives us full parallelism and full sharing of resources. So this is a way that we can reduce the memory footprint, saving CPU. The solution that we have for NVMe over Fabrics is using NVMe over Fabrics target offload for saving CPU cycles. As I show you earlier, that there is good mapping between NVMe queues and NVMe over Fabrics queues that using RDMA, and we have hardware that can receive an NVMe command capsule and encapsulate it and decapsulate it to NVMe protocol and post the request through the PCI bus without any CPU interference. We have numbers, I summarized the numbers that we get from our testing in ConnectX 5. We get 1 million IOPS, and in Bluefield system on chip we get 7.5 million IOPS without even one cycle of CPU. The target, as I said, receives the packet from the initiator and posts the NVMe command. It translates the NVMe over Fabrics command to NVMe command, post it to the NVMe submission queue, and generate NVMe over Fabrics response capsule when the NVMe device finishes the command. So upstream submission is still ongoing. I cannot estimate when it will be submitted, but the solution is available in Mellanox software package, and also there is a Linux fork that I maintain in the Mellanox GitHub, so you can also use it and take it as a reference. So why it's important? It's important because we want to build cheaper storage systems, and this can save us money with buying cheaper CPUs. So here I demonstrate the data path that is used with non-offload target. The ConnectX or other device receive the packet from the wire and send an interrupt to the kernel, and the kernel processes the data and applies a block request. And in the offload solution, we don't raise an interrupt. We just put the command to the NVMe device without any cycles of CPU needed for processing. This is a summary for the Linux block storage protocols and features that are implemented in the Linux block storage. I compared here NVMe over Fabrics, ISER, and the SRP drivers. The first feature is fast memory registration. We must have it in all of the drivers. This is the basic of RDMA. Indirect memory registration, we have implemented it in ISER and also work in progress in NVMe over Fabrics and in SRP. Shared receive queue is implemented currently in the NVMe over Fabrics target and in the SRP target. I hope that we have the bandwidth to implement it in ISER also soon. Shared receive queue per core or per completion vector currently is work in progress in NVMe over Fabrics. Also, we hope to implement it in ISER and also in SRP. Remote key invalidation currently is implemented in NVMe over Fabrics and in ISER. The block multi-queue, a very important feature. It's a block layer feature currently implemented in NVMe over Fabrics and in SRP. ISER has a little bit problems with that. I don't think it will be implemented in the near future, but we have NVMe over Fabrics for it, so it's okay. Rocky support. Rocky is a RDMA over Converge Ethernet. It's supported in NVMe over Fabrics and in ISER. Currently, it's work in progress in the SRP protocol. There are patches that the maintainer of the SRP driver, Bart, posted to the Linux community. and I think they will be merged soon. User space tools, we have NVMe CLI and NVMe TCLI for NVMe over fabrics. We have iSCSI admin and target CLI for ICER. And we have the SRP daemon and the target CLI for SRP. High availability, DM multipath is supported for all the three block protocols. For NVMe, we have the NVMe multipath that the previous talk explained about that. T10PI, it's a feature that gives you a protection information from end to end, from initiator to target. Currently, it's implemented in the protocol of ICER. I hope we will implement it soon in NVMe over Fabrics. It's an important feature, and we will do it soon, I hope. User space, open source target. We have SPDK for NVMe over Fabrics, and we have TGT target for ICER. For SRP, there is no user space target currently. I don't know if it will be implemented soon. Okay, thank you.